Dobry wieczór. Меня зовут Bob Ippolito. That's all the Russian I know. The rest of the talk will be in English. If I'm going too fast, please let me know. The slides are published online, so you'll be able to look at them later on if there's something that you missed. So why a talk on random choice? Well, to be honest, I was rewriting an IRC bot. We had an IRC bot at Mochi Media who would just sit there and he would learn from what other people said in the chat. And so his brain was based on this statistical model called Markov chains. And these Markov chains would be based on all of the words that have ever been said. So based on the frequency that the words occurred, he could build sentences that looked almost like real English. But of course it was gibberish because a machine was choosing words randomly. And so random choice is essential to this application, but also many other applications. And Markov models were developed by a Russian mathematician, Andrei Markov. And the basics behind a Markov chain is it's a map of state transitions. So in this diagram, you can see from the state E, there's a 30% chance of returning E again, and a 70% chance of returning A. And there's also the state transitions from A. I don't really have time to go any deeper into this. I just thought I would show it because it's interesting. And so really, what is this? Well, it's not just for IRC bots. Most ad servers also use random choice. And I'm very familiar with ad servers, at least one of them, the one that we built at Mochi Media. And the most interesting part of my research for this talk was to come up with an efficient way to do it. There's many different ways to do it, but it is tricky to find a way that is efficient, that doesn't use a lot of memory and doesn't use a lot of CPU. And just a quick aside here, I will be using Erlang's random module as a demonstration for this talk. But the random module is built on a very old algorithm, and it's actually not very good at all. It was designed for 16-bit computers in the early 80s, and it has bad results. So if you're writing your own application that depends on random numbers, I would suggest using the random number generator in the crypto module, which generates cryptographically secure random numbers, although slowly. But there are third-party libraries, such as a Mersenne Twister library that is actually quite fast and relatively competitive with this very old algorithm, speed-wise, but of course much better quality. So despite all this, I'm going to use random for the examples because it's built in and it has a simple API. And so the basic uses of this random module are to generate uniformly random numbers. And that is a number between 0 and 1 uniformly throughout the whole distribution. And you can use this to simulate things like flipping a coin. So in this example, when I generate a number less than 1/2, I'll show heads. And when it's more than that, I'll show tails. And this is just a quick demonstration of what it would look like. The X at the top is the number that was generated from the uniform random number generator. In this case, it's actually implemented in JavaScript. This isn't using Erlang, but it demonstrates the technique. So you can see about half the time it's heads and half the time it's tails. The other thing that you would do with a random number generator is to simulate the roll of a die. So in this case, I'll roll a 6-sided die, very, very typical that you'd find in any any like casino game or something like that. And to generate a random die roll, you simply multiply this uniform floating point by the number of sides of the die and truncate it. And you can see a simple implementation here. The random module does implement this. And this is just an example of what that looks like. You can see maybe that there's somewhat an even distribution of the different rolls. And to get a little more complicated, let's say you have a set of things, maybe not sides of a die, but some set of any elements. One of the basic algorithms you would do is random selection. Random selection without replacement means that once you choose the item, you remove it from the list. So let's say like names in a hat or something like that. And this is a simple version of that algorithm in Erlang. The code is very simple, not too interesting. And here's an example of how that might look. And so at the bottom, you have the list of elements that it's choosing from, and at the top, the selections that were made. You can see that each element of the list is chosen only once. So essentially what we're doing by choosing all the elements is shuffling the list. And the other thing that you would do that's very similar is random selection without replacement. And what you do here is, this is weighted random selection without replacement. This is just an example of the algorithm. I'm not going to go into it, but basically you take, for each element of the set, you also give it a weight, and then you walk the list until you find the element that is that far down the list by weight. And so an even simpler algorithm is random selection with replacement. So this means, given the original list, you simply choose an element from it without mutating the list at all. This is the same as rolling a die. And here's an example of what that looks like. We have our list with 6 elements here. Each time I select one, the list remains unchanged. And so I'm selecting them randomly. You can see that I'm getting the same results more than once. And so to implement this algorithm, this is the algorithm that is used for things like Markov chains and most often in ad servers. So with replacement, the weight can be implemented very simply. This version, you just add the item to the list multiple times. So in this list, I have A 3 times, B once, C once, and D once. And this means that half the time, A will be chosen, and about 17% of the time, each of the other elements will be chosen. And this is what that looks like. You can see I have 3 snowmen, so they'll show up about half the time. Okay, maybe a little more than half the time, but that's what random numbers are. So this time we see it's more like what we would expect, but because it's random, you can never know what the results are going to be. Only that if you generate a huge number of results, then you expect it to look very close to the probabilities that you gave it to begin with. The problem with this solution is that it's not very memory efficient. So you can see in the previous slide, I have the snowman there 3 times. So if you imagine 1 million snowmen in there, you'd have a very big list. So you can do better by counting each key uniquely. So this is a representation of the same data, but I have as the first element the total count, So A was there 3 times, B once, C once, and D once. So the total is 6. And then you can see each element with the number of times that it occurred. The trade-off with this model is that it's harder to seek to the nth choice. With the previous algorithm, we can just simply go to that index in the list or the array, which can be very fast. But in this case, we have to walk through the whole array or at least some subset that could be as large as the whole array to find it. And one clever way to do this is called the alias method. And the alias method combines the technique of rolling a die and then flipping a coin. The interesting thing here is that it uses only ON memory, but it also has O1 selection. So you can generate a selection using this kind of data structure with only one step, completely independent of how many elements you have. And here's an example of what that looks like. So first you roll the die to see which element in your table you look for, and then you flip a coin to see if it's the left or the right. So first we see that the die roll was the first row, and then the coin flip was to the head. The way that this data structure is built, the first entry is typically going to not have any data in the tail because the probability is 1. If you add up all the probabilities, you'll see that they're the same as they were originally. Half of the total belongs to A, and the 1/6 belongs to each of the other elements. But the problem with this data structure is that it's not efficient to handle updates. For our IRC bot, the choices update for every word of text. And the alias method is ON to update. So when you update this table, you have to go through the whole data set and sort it in a specific way to come up with these probabilities. So the problem with this method is, although it's very, very efficient if your list of things to choose from is fixed, it's not very efficient if it changes frequently, because it creates garbage of the whole set. So you'll run into problems where your process is garbage collecting frequently. And you can work around this by using a tree to represent your choices, which provides you with fast updates, low amount of garbage, but the problem with a tree is it has very slow seeks, because your tree, when you walk it, it's sorted by key. But really, you want the most frequently chosen items to be first in your search, so that you can seek faster than that. And the solution that I ended up implementing was basically a Maxi. It seems to be a pretty good compromise between speed and memory. Essentially, this is just a list where the highest weights are first on the list, and the trick here is that the highest weights are most likely to be updated. So when you update something near the beginning of a list, you generate very little garbage. The problem is, of course, the worst case is ON. Basically, you recreate the entire data structure for an infrequently seen word. But it has a very good common case, and it's much better than the alias method, where you have to recreate the entire data structure every time. And this is a simple example of what that might look like. So I have the character A that happened once, B that happened once. I put it on the top to minimize the amount of garbage collected. And if I enter A again, it'll move to the top of the heap. So basically, this as you generate lots and lots of samples, it'll move the most popular samples to the top, and you'll be able to choose them very quickly. And so to choose it, you can see the pink ones are all of the elements that it had to look through, and the darker one, the red one, is the one that was chosen. This is an example of the worst case. But if I put in A lot more times, we'll see that often it doesn't have to look very far. And in our data set, it looked like this most of the time. And that's pretty much it. I didn't have a lot of time, and I've been enjoying Moscow the past few days, so I wasn't able to put in as much effort as I wanted to. But I'm happy to answer any questions about this talk or Mochi Web or anything else, really. Thank you.
Any questions?
Instead of random uniform, have you considered using Erlang phash of Erlang makeref? I mean, makeref always produces unique results, and Erlang phash guarantees you the limit you want to have in integer, not float, of course.
Well, that hash algorithm it actually generates relatively few bits, maybe 32 bits. So in this case, it's actually even worse than the ancient random number generator.
Well, yeah.
In that one, combining three 16-bit numbers, it has about 48 bits, a little less because of the numbers that are chosen. And the other thing about using a hash is that it's not uniform. So in order to accurately represent these probabilities, you really do need a uniform random number generator.
Fair enough, thanks.
Hi, Bob. So my question is that if you speak about showing advertisement, you also need some storage for it. You need to track each to track how many times you have shown any advert. So speaking about Erlang structures, there may be some other problems which you can meet during solving this problem. So maybe use other structures, for example, ETS or DTS Amnesia or some other database. So what can you say about it? Maybe you need to adopt to use ETS structure for these tasks. And also, if we speak about advertisement, you have a lot of clients that you want to show on this place, and so changing a big list may be too expensive by memory consumption. So what can you say about this problem?
So with this, for a large ad network, of course you would use some sort of probably key value store such as ETS, or maybe something more persistent with in-memory cache. But in order to choose the advertisement that's shown, you need to find one randomly. And if you have 10,000 possible ads, iterating through them all in ETS might be slow and also generates a lot of garbage. In our case at Mochi, we had some in-memory data structures that represented this list of possible ads. Although, of course, it's slow if you update it for every client, but if you batch the operation for updates, it's not as slow. And the size of the data structure is based on the number of ads in the system, not the number of possible clients. So that's usually much smaller.
So, but under clients, I meant those people who pay you for showing money, not by visitors.
Okay. Yes.
Okay. Okay.
The goal was to build the chatbot here.
Yes, the goal was to emulate a feature that this chatbot had.
And as far as I know, Markov assumptions work well for English and not for any other language. Something for Russian, for example. Have you tried some other language models like Pancreas and so on?
I have not. It was just an old IRC bot that was built for amusement, not for research. In this case, the choice of Markov chains was already chosen because we had an old version that I was simply rewriting for performance and education reasons. So we have years worth of data stored in this Markov model.
Thank you.
And was that old version mega hell or something other? Old version of the bot, ancient mega hell.
I'm sorry, I don't understand.
That is the name of some IRC bot that produces Markov chains phrases actually.
Oh no, this was
that was just of curiosity, question of curiosity.
Okay, this is it was a custom IRC bot written back in 2007 in Python by an early Mochi employee.
Well, thank you.
Bob, it's again me, and I have other question. For example, if you want to make a weighted distribution between different choices, currently you have shown problems with simple random uniform function, which is known to be vulnerable to attacks, for example. But if we use crypto rand bytes, we can get a very big number of data, which is rather good. It is really random, and you can think about some mapping function from this data. For example, from each 4 bytes of this data or each 8 bytes of this data to some space of your weighted distribution, and for example. Modular division or some other function, and use crypto round bytes to find which choice do you want to use next. Have you thought about it? Have you some ideas?
Yeah. So the most simple way to convert random bytes to a uniform float between 0 and 1 is to simply generate maybe 64 bits and take the low 53 bits and use that in a floating point number, and that's equivalent to any uniform random number generator that returns a double. So that's a very simple transform. There are other transforms that you could do that maybe avoid floating point math, but using a double is typically the easiest, unless you do need to generate a choice out of a list that actually has much more than 53 bits. At Mochi, we used crypto rand bytes, and we generated a very big number, and then worked with it in fixed point. Like maybe we generate 128 bits and then divide by some number. Actually, we'd multiply all the weights by some number so that the weights would all be integers.
Okay, and now we have a short break, I think, yeah? For coffee.
Thank you, Bob.